What is a transfer function in mechanical engineering? Have you ever wondered how engineers predict how machines respond to forces? One key tool they use is the transfer function. This mathematical expression connects the output of a mechanical system to its input. It is often represented in the Laplace transform domain, which helps in analyzing how systems behave over time and frequency without getting lost in complicated equations. Mechanical systems, like the classic mesh spring damper setup, follow specific rules. These rules come from Newton's laws of motion. For instance, consider a single degree of freedom system with mass, damping, and stiffness that reacts to an external force. The equation of motion for this setup looks like this. Mass times the second derivative of displacement plus damping times the first derivative of displacement plus stiffness times displacement equals the input force. To find the transfer function, we apply the Laplace transform to this equation, assuming there are no initial conditions. This process turns the time domain equation into an algebraic equation using a complex frequency variable. The resulting equation shows how the output displacement relates to the input force. When we rearrange it, we can express the transfer function as the output over the input. This transfer function captures the dynamic behavior of the system. It shows how the displacement output reacts to the force input across different frequencies. This is particularly useful in system dynamics and control, as it simplifies the analysis and design process. Engineers can predict how a system will behave, design controllers, and analyze stability without repeatedly solving complex equations. In mechanical engineering, transfer functions can describe both translational and rotational systems. Translational systems involve linear motion, using components like masses, springs, and dampers. On the other hand, rotational systems deal with rotational inertia, torsional springs, and rotational damping. Both types can be modeled using transfer functions derived from their governing equations. In practical applications, transfer functions play a vital role. They help design vibration isolation systems by analyzing how inputs affect outputs. They are also crucial for developing control systems for mechanical actuators and robots to achieve the desired motion. Additionally, they allow engineers to predict resonance frequencies and damping behavior, which is essential to prevent mechanical failure. Moreover, transfer functions simplify complex mechanical-electrical system modeling. By representing components as transfer functions and connecting them in block diagrams, engineers can create a clearer picture of the overall system. In summary, a transfer function in mechanical engineering is a fundamental tool that expresses the relationship between input forces and output responses of mechanical systems in the frequency domain. This enables efficient analysis and control of system dynamics, making it an essential concept for engineers in the field.